How's it going, Nick?
It is going fantastic. Another lovely day in sunny San Diego. It's too sunny.
A little too sunny. A little too sunny, I will say.
It is far too sunny. I'm toasting in here. I got two fans on. It doesn't even matter.
Yeah, it's all about that circulation of air, you know what I mean? Gotta keep the
It
window
is.
cracked open.
It's cracked.
That's tragic,
It's
Ben.
cr-
That's tragic.
it's cracked. I promise. Yeah. It's like me at Fortnite.
Yeah,
Cracked.
I've yet to confirm that fact, but maybe, maybe when we have some free time next week, after all these guys are taking their MPE, you can run some.
Yeah. We'll run some duos for sure.
Yeah, for sure, for sure. Cool.
Hello and welcome. Uh, in case you didn't see the announcement, today we're going to be talking about, um, broadly speaking, functions and their respective graphs, how to graph functions, a little bit about inverse functions, transformations. We'll see some of the stuff we've already talked about, but this is on trying to build a connection between equations, coordinate pairs, and graphs, and hopefully we can sort of build on that. I know there's going to be a lot of, um, or at least there is likely to be a good amount of graphical interpretation, stuff that relies on this connection. So hopefully this will be a good refresher for that. Rishi, do you want to add anything?
No, nothing in particular. Yeah, I mean, today is going to be, um, hopefully we'll get through all of functions. So, exciting news. I mean, we only have two modules left. Um, and yeah, thank you guys for being here. Um, I believe Nick, you'll be starting us off, but before that, just a quick little, let's get a quick little breakout room for today. Um, classic here, classic a little icebreaker. Let's do a game of two truths and a lie. Okay. Get you guys learning about each other. So as a reminder, two truths and a lie. You're gonna type out or verbally say three facts, one, two, and three. And one of those will be a lie, and two of them will be truths. And we'll go through, and if there's time, you can try to guess what the lie is for everyone else. So try to go one at a time. One person says their three facts, and then everyone else makes their guess. And you can see who is the best guesser of the lie. So I'm going to go ahead and make a couple breakout rooms here, just for about 10 minutes, and then you can bring it back at around 2:43, 2:44. Cool. Cool. Rooms are open. See you guys in about 10 minutes.
All right. It looks like one of the rooms only has two people in it, so I'm gonna hop into that one.
Yeah, I assigned you to that room.
Oh, my iPad. You said my
Oh, your
iPad.
iPad? Okay, okay.
Yeah,
I
Nick
tried
Ratto
to.
iPad mode.
Okay, okay. Yeah, I'm gonna hop in a room as well. But yeah,
All
sounds
right.
good.
You know, chest down. They don't know what's going on down there. You could be limber. Be super
Sure, I
limber.
could be limber. I could also not have legs. Like that could have been my lies. I just don't have legs. Or I guess
Really, that could
that
have
could
been
have been
it.
true.
Then you cannot do the splits by definition.
Sure. Well, hopefully I would have had to have legs because one of my facts was I could run a mile in under 5 minutes and 20 seconds. But
Yeah. Is
surely,
that and that's
surely,
true?
yeah, that's true. That's true.
Wow, that's fast.
Thank you, man. I know,
Good
you're a
stuff.
big basketballer. I'm sure you've got the endurance as well. We should race sometime.
I'll race you. I'll smoke you. All
Oh,
right. let's get to it. Let's talk about functions and while we're at it, talk about the graphs. Okay. Let me put do not disturb on. Get my vitamin C, and let's do it. Okay. So, the worksheet is posted in the Discord server. Um, if you haven't already gotten it, make sure to download that. If anyone does not have access to the Discord or anything, or they need it to be posted in the chat, uh, maybe Rishi, you could put the PDF in the chat. But okay, let's get into it. We're gonna start off by talking about exponential functions. This can be our first mention of these guys, and these will come up in our last two modules. An exponential function by default, or by definition, not by default, is anything that has a variable in the exponent. So for example, x squared is not an exponential function. That's a polynomial function. 3 to the x, however, is an exponential function. And the general form of these guys is some constant times a base to the x. Now, what does it actually mean? What do these parts actually mean? Well, we can think about it as we're raising this base b to a power, right? As we change the power, the base is the thing that's getting scaled by this power, right? So we can think of it as if we plug in x equals 1 all the way up to x equals 10, right? The larger b is, the more it's going to have grown in that span, right? You're raising a larger number to a larger power. That makes sense. However, this only works if your number is greater than 1, right? If your number is not greater than 1, uh, then you're not going to have this exponential growth. You're actually going to have what we call a decay, right? We can picture multiplying 1/2 times 1/2 times 1/2 times 1/2. It's going to get smaller and smaller and smaller instead of bigger and bigger. And so we have this general rule that sort of determines what graphs look like, exponential graphs, where the base determines the shape. So if the base is between 0 and 1, then increasing x is going to make it go towards 0, so we have a decay. Uh, on the flip side, um, negative powers, which remember x, for example, to the -2 power is equal to just 1 over x to the second power. Then we can picture as this number gets really small, that fraction is going to get really big, right? So for small bases, the negative powers are going to be the ones that blow up, whereas the positive powers are going to go to 0. Okay. Then for growth, basically any number that's greater than 1 is just going to shoot off to infinity as we increase that exponent. Let's see. If I'm trying to think, if the base is negative, what that looks like. Um, I might have to get back to you on that. Rishi, can you think what happens if the base of an exponent is negative?
I want to say it's just to flip across one of the axes. I mean, you could plug in a couple numbers right now just to test that out. No,
That's true. That's
just
true.
try like f of x
Uh,
equals -3 to the x.
do I have Desmos on here? I'd actually like to.
Yeah,
Oh, I
yeah,
do have
for sure.
Desmos on here. All right, let's check this out. Let's learn. Because I don't remember off the top of my head what this is going to look like. If you have, for example, -2 to the x, I don't know what's going on here. Is it just not plotting? What if I plot 2 to the x? Okay. So it seems like it just doesn't plot. I guess it kind of makes sense because, you know, if you plug in a negative number to an exponential, any even power you raise it to, it's going to be positive. Any odd power is going to be negative. So I can imagine maybe it's doing some jumps back and forth, but I don't know why it wouldn't plot. So I guess for now we won't consider negative bases. That's a point of research. Um, but yeah, so there's these growth and decay models that are based on what the base is. And there's a couple ways you typically see these exponential functions represented. Um, this is the model we've just talked about, some constant times a base to the x. Um, a lot of the times you'll see stuff like this. This is the equation for um, annually compounding interest, where A is some amount that every year or once every time period grows by some amount. That percent is given by R. And then a lot of the times, the most common exponential you'll see is with the base E. Which E, for those of you that don't know, is sort of a pi-esque number. It's irrational, 2.7182818, and then a bunch more uh digits. It does not repeat like that. It just looks like it repeats for the first couple numbers. Um, but E is a number that you're gonna see a lot, especially as you get further into math, especially in calculus. Um, and it's big in exponentials. So a lot of the times you'll see stuff like this, where we have here's some constant times E to some constant times T. Um, these are all just common things that when you see them, you can recognize, okay, we're looking at exponential function. And then the converse exponential decay formula for each is listed next to it.
Cool.
Okay.
Real quick.
Yeah.
Yeah. Well, first of all, I just want to say I'm very impressed by how many digits of E you were able to recall
Well,
just off the dome. That was,
it's like 4 digits just repeated.
dude. I mean, you had me at 2.7. I was like 2.72, and then that's about it. But
Yeah.
I did want to say, so yeah, y equals -2 in parentheses to the x is impossible to graph, kind of like what you described. It would be jumping back and forth. It's a discrete function, so you can't really like it's impossible to graph it. However, y equals -2 to the x, right? So there's no parentheses, just like a negative times 2 to the x, such as that, yeah, will be just the same graph as y equals 2 to the x flipped across the x-axis. So it's going to be like a downwards, yeah. So yeah, we learned a little bit. It makes sense too because that negative is rather than being attached to the two, it's being attached to like the entire thing. So it's just going to be all the y values are now negative.
Yeah. Okay, cool. We learned. I wasn't fully sure either, so that's cool. Okay, cool. So these are just some common forms you'll see of exponential growth and decay. Um, then getting into one of the most stereotypical and sort of applied mathy approaches to looking at exponentials is interest, where I mean, the main example of this, if you've got money in an account and that account promises you some percent return over a period of time, then usually you'll be able to model that with some sort of exponential growth function like this. Um, Now, the compound interest formula here, we can break up into its parts, um, where P is the original amount of money you put into the account. R is the total rate that you are promised by your bank, the rate that they say they're going to apply for interest. A lot of the times this is given as like a percentage, like 5% or something like that. Um, N here is the number of times interest is compounded per year, and T is the time in years. Now compounded interest, what that means is maybe you have a bank that, and we'll see an example of this in a second, but maybe you have a bank that promises you 5% returns, uh, compounded annually. And what that means is that once per year, you're going to get once per year, you're going to get 5% just added on to your original amount. However, a lot of banks, what they do is they compound monthly or quarterly, where you apply some fraction of that 5% every period that they specify. For example, quarterly would mean that you gain whatever a quarter of 5% is once every 3 months. And so that happens 4 times. And in the end, I guess the percentages add up to 5. But actually, as we'll see, the more often you compound interest, the more frequently you do that, it's actually better. You'll end up with a larger amount of money than if you compounded less frequently. But that is where this equation comes from. In practice, a lot of the times it'll look like whatever amount times 1 plus maybe 5%. If you want to do it monthly, you would divide that 5% by 12 and then raise it to 12 times t, where t is in years. Okay, cool. All right, another common application of exponential functions is in the half-life of something. This is big in chemistry, used all the time in like fossil records, uh, anthropology, archaeology, stuff like that. And it is the amount of time it takes for a quantity of a substance to decrease to half its initial value. Now, naturally, it makes sense for when it's reduced to half its value, the equation's just going to look like this, right? But leading up to that half, right, it's still decaying, right? So the way we model this is we multiply by 1/2, and then we raise it to a power of t over the half-life, such that when the time elapsed reaches the half-life, that exponent simplifies to 1, and you're just left with this n times 1/2, right? But as we creep up to that 1/2, we're losing a bigger and bigger fraction up to that 1/2. So that's where this equation comes from. That's why we have that fraction in the exponent. We just want to know what the fraction of the half-life is for time. Um, cool. All right, does that make sense? Why we have it as a fraction and not just a number? It's a pretty all right. It's a pretty common practice, especially in like physics, um, where you'll have some like reference time that you want your exponent to simplify to 1 at. So you'll just do t over that reference time. Okay, cool. All right. Now just by looking at data, uh, sometimes you can identify what kind of function we're looking at. More than just exponential. I'm sure you've done this before. You can look at a set of XY pairs and try and fit a curve to it. This is really useful in statistics, in lots of fields in engineering, where we want to sort of draw a line that represents a set of data as best as possible. Um, the way we analyze what kind of function we're looking at is we try to look at the difference between each subsequent step and how that changes between steps. Um, for example, if we look at table 1 here, at x minus 2, we're at y minus 4. Going to the next step, as we increase x by 1, we increase y by 3. To the next step, increasing x by 1, once again, increases y by 3. And we can see this pattern repeats itself all the way down. Now, if it's increasing by the same amount every single step, what type of function are we looking at? Feel free to type in the chat. Yeah, perfect. We're looking at a linear function, right? The same slope upwards. Every time we go over 1, we're going up 3. So if you see it increase by the same amount every time, you know it's linear. Table 2 here, we have x minus 2 has us at y equals 0. Then increasing x by 1 decreases y by 3. Increasing x again decreases y by only 1. Then increasing x by 1 actually increases it by 1. And increasing x again increases it by 3. Can we try and picture what are we graphing here with these data points? It does resemble an exponential in terms of like the rate of change itself is different between steps. But we can actually, it's different in a very predictable way. At first, we're going down by 3. At first, we're going down by 3. Then we're going down by 1. Then we're going up by 1. Then we're going up by 3. So, in fact, in terms of these guys, the rate of change itself is actually increasing by 2 every time. And the rate of change is increasing at a constant rate. This is a quadratic. So good for you guys that got that right. Um, for those of you that have done calculus, you don't have to know this, but you may be able to identify the derivative of a quadratic is linear, which would mean that the rate of change is increasing at a constant rate, which is why we see this characteristic. But if your rate of change is increasing by a constant amount between each step, you have quadratic. For table 3, here we have increasing x by 1 goes up by 0.25. Then we get an increase from 3.5 to 4 of 0.5. Then we get plus 1. Then we get plus 2. Now, what does this look like? Yeah, this is exponential. The way we can tell that is the rate of changes getting multiplied by 2, getting multiplied by 2, getting multiplied by 2. We have a common multiplying factor rather than an additive factor that repeats each step. So we could actually take that factor and figure that this function is going to look something like 2 to the x times something plus something, right? Um, In fact, this looks like 2 to the x plus 4, maybe. No, 2 to the x plus 3. Um, yeah. I figured that out, by the way, by if you plug in 0 as the exponent, 2 to the 0 is 1. We know that the y-intercept is 4. So plugging in 0 should give us that the factor we need to add here is 3. Because 2 to the 0 plus 3 gives us 4. Okay. But that's sort of how you can determine um, what type of function it is just by looking at the points. And that sentiment's echoed here. If the value is staying the same between steps, it's linear. If the value is changing, but the differences of differences are the same, it's quadratic. That is referring to this guy, the plus 2 being constant each step. Um, and then if the value is changing and the ratios between two values are the same. And so that's like exponential. The difference in each one is scaled by a multiplicative factor. Okay, cool. Does that all make sense? That's sort of how we can see uh, what different functions look like just by looking at their points. Cool. All right. And remember, if things don't totally make sense now, or if you have any questions, feel free to message or stop by. I had my office hours earlier. Rishi has his office hours right after this. So feel free to stop by, ask any questions. Okay, let's do some examples. The first one is to kind of try and illustrate uh, what compound interest is and why it's more beneficial to you to compound more often. Okay, so if Gloria places $5,000 in an investment that pays 5% interest compounded annually, she would like to know what happens for the first 4 years of her investment. What if it were compounded quarterly? Okay, cool. So if we think about annually, what we're actually modeling here is what happens to this $5,000. Now, after the first year, as it says in the problem, it gains 5% interest. What this looks like is multiplying by 1.05, right? Okay. After the second year, whatever money that was left over after the first year is once again uh has 5% interest on top of it. This is the money left after the first year. So this is the amount that's scaled by 5% after the second year. After the third year, we get one more factor. After the fourth year, we get one more factor, right? So we get 5,000 times 1.05 to the fourth power. And that is our annual interest equation. It's just whatever percentage to the power of however many years times our initial amount. And that's going to equal something. I haven't calculated it. Because I read the problem wrong when I was making the answer key. Oops. So I'll have to adjust the answer key after this. All right. Quarterly, we have our initial amount times, and what this is going to look like is every 3 months or 4 times a year, we are going to get 1/4 of 5%. So 1.25%. So 1.0125. So after 3 months, it's scaled by that. Then after another 3 months, this factor entirely is scaled by that 1.0125 again. And after the next 3 months, it's going to happen again. And in total, the amount of times this is going to happen is 4 times the number of years we're dealing with, right? Because for every year, we're doing it 4 times a year. So we have 4 times 4 for 4 years. 5,000 times 1.0125 to the 16th power versus 5,000 times 1.05 to the 4th power. So let me open up a calculator. So this number is going to work out to be oh my goodness. One sec, sorry. So this number looks like it's going to work out to be $6,077.53. If we were to do it the other way, we would have $6,099.45. So the difference isn't huge. I mean, maybe you'll be able to afford 1 or 2 more lunches with that amount of money, uh, by choosing the one account over the other. But for very large amounts of money, you can imagine this difference being a lot bigger. And point being, as you compound more and more frequently, then you're going to get better returns. So what is the equation that models this? Well, if we use P as our amount and P sub 0 as our initial amount, that's like the $5,000 in this problem, then what it's being multiplied by is 1 plus the total rate. In this case, we had 5%. That's divided by the number of times it's compounded annually. In our problem, it was 4. That's why that whole thing simplified to 1.0125. Then we're raising it to the power of the number of times it's compounded annually times the number of years it's been running for. And so that's where that equation comes from. That's why it's so useful for stuff like this. And interestingly, there is, and I'm not going to do it now, but if you're interested, you can look it up. There's actually a nice proof for, or a nice derivation of the constant E that has to do with this, where if you took 1 plus 1 over n to the n, so essentially if you compounded infinitely often, like every single instant you compounded, a tiny fraction of 100%, and you let n go up towards infinity, it actually tends towards the constant E. So E is very tied to exponential growth. And this formula actually can produce the constant E if you do that. But that's besides the point. Don't worry about it. Okay, cool. All right, we'll do this next example. And we'll try and figure out what kind of function we're dealing with. Okay. So if we look at the difference in y as we go up by 1 in x, you can see from -2 to -1, we go up by 1/2. From -1 to 0, we go, oh, I'm sorry, up by 1/4. Next step, we go up by 1/2. Next step, up by 1. And then next step, up by 2. We recognize this kind of equation, this kind of function. What are we working with here? Beautiful. I love the chat right now. It's all just the word exponential. Yeah, so this exponential. As we can see, the factor that's linking each step to the next one is 2. So we have some function that's 2 to the x. Um, Now it looks like plugging in x equals 0, that we get 3 as our output. Plugging in x equals 0 to this gives us 1. So if we add 2, we can check if this is the shift we're supposed to get. Plugging in -1, we get 1/2 plus 2 is 2.5. Plugging in 2, for example, 2 squared is 4, plus 2 is 6. So this looks like the right function. Okay, cool. Now, I'll probably only do one of these just for the sake of illustration, but this is a technique that's especially useful if you want to graph a function. Um, to graph a function, you need points, right? And a lot of the time, to sort of get an idea of what a graph is going to look like, a great approach is just finding some points and plugging them in, seeing what they evaluate to. And so let's see how this function translates to points. The first thing I notice is we have an x minus 4 in the exponent. Can you guys predict how does that being an x minus 4 instead of an x, how is that going to change what our graph looks like relative to if it was just an x? Oh, sorry, maybe I lagged. If does it cause? I see, because the negative. Um, it won't be a reflection. Um, think of in the past what has happened when we've taken our input x and added or subtracted something to it. What happens to the graph? It does shift. Um, in this case, it should shift to the right. The reason for this is imagine you're plugging in x equals 5, right? You want to plot your graph at x equals 5. Um, Now, when you plug in a 5 to this, it's going to essentially turn that 5 input into a 1 input. So the value at x equals 5 is the value that would normally be at x equals 1. It's just been shifted 4 to the right by this subtraction. So that's why adding and subtracting numbers to the input shifts it, because it's essentially taking the whole graph, the value that would be at one point, and then shifting it by that amount. And we can remember that subtracting a number from the input is going to shift it right, and adding a number to the input is going to shift it left in the negative direction. So if we figure this is going to shift it right, then I say we should probably plot points around x equals 4, because that'll sort of be where we normally would have had x equals 0 will now be centered around x equals 4. So I'm going to plot points 2, 3, 4, 5, 6. All right. And we can just go ahead and plug in each one. I'll start with x equals 4, because that's going to make the exponent 0. So we'd have 3 times 2/3 to the 0 power, which is just 1. So at x equals 4, we just have a value of 3. At x equals 3, we have 3 times 2/3 to the minus 1, 3 times 3/2, or 9/2. Okay. Plugging in x equals 2 is the same as, it's going to be the same as multiplying this number by another factor of 3/2. So 27 over 4 should be what we get when we plug in x equals 2. Plugging in x equals 5 is just going to be 3 times 2/3 to the 1, which is just going to be 2. And then plugging in x equals 6 should just be 2/3 of the previous one. So it should be 4/3. Okay. Noticing the pattern in the y column, do we have growth or decay from this function? Yeah, it should be decay, right? The numbers are getting smaller as we increase x, so it's decaying. And we could have predicted that by the fact that the base is less than 1. It's 2/3, so it's going to get smaller and smaller. Okay. We could plot it. I mean, broadly speaking, the graph's just going to look like that. And because an exponential can never equal 0, it's going to have an asymptote at y equals 0, where it slowly approaches that value. And then, axis is going to be something like that. I don't know. It'll probably be out here. Okay, cool. So that's, I think, a pretty good technique for just kind of visualizing what a function is going to look like ahead of time and actually graphing it, getting useful information. Cool. I'm not going to do the second problem. I think it would be good practice and it's worth looking at in your own time, but I think maybe I speak for everyone when I say maybe we took a little too long on those. So in the interest of time, we'll move forward and I'll pass it off to Rishi to round us off.
Cool. Thank you, Nick. Good stuff. Good stuff. Um, let's transition to my screen here.
All right.
So, we are going to be talking about, as the name implies, Module 2, which is going to be functions and relations, which are just going to be two vocab words for us. We're going to take a look at a few different functions, and we're also going to be talking about inverses, which is a little bit of algebra, which is something you're going to want to know how to do for the MPE. So the first thing is a little bit of vocab, as I mentioned, functions versus relations. A function uh, is pretty much just an equation. So we're given an input, such as x, and then we have to find the output, such as y. So one rule for functions is there can only be one input for every, one output for every input. You can't have multiple outputs anytime you plug something into the equation. And so the way we kind of test that and make sure that something is a function is through the vertical line test. The vertical line test is that you test that something is a function by drawing a vertical line and anywhere in the graph, any domain of x, so anywhere across that like entire graph, the whole width of it. If you draw a vertical line, if you draw one here, if you draw one here, if you draw one here, you should only run your pencil across one point, right? There shouldn't be multiple points on that line. So anytime you draw a vertical line on a graph, not like you're actually graphing that line, but just to test, you should only have one output, which is different from a relation. So the second vocab word is relations, which is a set of ordered pairs. So this is similar to functions in that we have inputs and outputs. We could still have x and y, or you could have coordinate pairs such as 0, 5, 4, 3, 5, 0, whatever it is. However, a relation is different in this sense that it's a little bit more lax, right? In this, we don't have to pass the vertical line test. As you can see here, we could draw a vertical line in many different places and have multiple outputs. And so relation is just a mathematical term to describe anytime you're looking at inputs and outputs and it's not a function. Primarily, we're going to be looking at functions. That is what we're going to see a lot in pre-calculus as well as in calculus. Relations don't come up as much, but it's still a good vocabulary to know. Speaking of functions, there's a whole bunch of them. There are some drawn out here for you, and there's a great many more, which you're going to see over the years. As engineers, functions are going to be crucial in describing the relationships between inputs and outputs, right? Anything from the way the position of something will affect some metric, um, such as I, I mean, let's see, a thing I might see is the metric of something might relate to the distance between two things might relate to their speeds in some sort of system. You might think about how the temperature of something relates to the efficiency of the system. I mean, there's any number of inputs and outputs that you could see in engineering, depending on what type of engineer you are. But we are going to start with the very basics. So I won't go through all of these, but we have seen most of these already. We have just a line, we have absolute value. We have quadratics, square roots, cubics, cube roots, inverses or reciprocals, rational functions, which we covered last week, logarithms and exponentials, which Nick got into, and then step functions, which are a little bit more discrete. Those ones are kind of interesting because it isn't continuously one line, but you'll note that it still passes the vertical line test. Any vertical line, even if I were to draw a vertical line here, you'd only have one point. If you look closely, I know it's really blurry. This is just an example, but A closed circle means that that point, whatever this point is over here, is included on this line, and this open circle over here means it's not included um, in this like little line segment right here. So a closed circle means it's included, open circle is not included. And then we have uh, trigonometric functions, sine, cosine, tangent. They all also pass the vertical line test. So note, you're not always going to see these functions in this format, but it's good to kind of familiarize with yourselves with these. And so just as me and Nick were doing earlier, or rather Nick was showing on Desmos, take your time to play around with functions, right? See what you can and can't do. For example, maybe you haven't seen this this guy over here, the reciprocal slash inverse slash rational function, right? Here we have graphed 1 over x. So ask yourself, I mean, what happens if you do 1 over x, or what if you do 2 over x? Or over here, we have 1 over x squared. Try to predict behaviors and play around with it. Just try to learn a little if you have some free time. The main thing I want to talk about for today is how to find the inverse of a function. Um, this is something that you're going to want to know how to do. It's a pretty short, I would say, a kind of like 3-step process. Anytime you have a function and you're trying to find the inverse, it's kind of like the opposite of that function. You're essentially going to be flipping over to the line y equals x, or x equals y, which that line is drawn over here. It's kind of like a diagonal line going from the bottom left to the top right of the graph. And so you can kind of see in this example, which is drawn out for us, we take a parabola and then we flip it to be like a sideways parabola. So how did we get that? How did we get that graph? Let's take a look at this example. 2y plus 3 equals x squared. So first things first, when we look at a function, it's best to put it in terms of either x or y. Usually we use the equation or the form y equals something, right? Y equals mx plus b. We might use y equals a x squared plus bx plus c. Anything like that. It's usually going to be a y equals. Y equals. And so step one is just put it into that form. Um, with functions, we usually use f of x instead of y. All that means is a function of x, where you can plug in any number for x to see what that result is. And so that's how you find your basic kind of function. Now we get to the part where you actually find the inverse. So step one is going to be swap x and y. Swap x and y. So here we have our x and here we have our y. They switch spots. Then step two, we solve for y, or resolve for y, right? Now we're going to be finding out what y will be. So I'll kind of show the work a little bit better here. Coming from this equation, we're going to do a little multiplication times 2 on both sides. So we'll get 2x equals y squared minus 3. Then we're going to add we're going to add 3 to both sides, which brings us to y equals plus or minus the square root of 2x plus 3, which is what's written out right here. There should be a typo on your page. The inverse it's saying is this, x squared minus 3 over 2, but that's in fact what our original function was. So go ahead and cross that out. That's not true. Our inverse is going to be the square root of 2x plus 3. It's going to be this little f to the negative 1. This little f to the negative 1, that's how we denote the inverse. It's f negative 1 of x equals 2x plus 3. And so you can see that graphed down here. However, I'll take a second and pause, but I'll speak through it. Um, just a quick note. Um, when we're finding the inverse of a function, we have to make sure it remains a function, right? So when you actually algebraically solve for y, you'll see that we have this plus or minus here. So what that means is you could have like this plus, this positive sort of half to it. You could also have this negative half, right? So this is like this is positive rad 2x plus 3, and this is negative 2x plus 3. So the inverse of the function is kind of both of those halves. However, if you actually put both of those on there, it's not technically going to be a function anymore because it doesn't pass the vertical line test anymore. Does that kind of make sense? So if you're actually looking for a function in your final answer, depending on, what the application of this problem is, um, you should make sure to maybe choose one half, either positive or negative rad 2x plus 3, in order to make sure that you're passing that vertical line test. Can I get a thumbs up in chat? That kind of makes sense. Cool, cool. Okay. So yeah, function, remember, definition has to pass the vertical line test. And yeah, I mean, that's pretty much how you find the inverse. Um, I know we just did the problem, but remember, step one, swap x and y. Step two, solve for y. And then step three, I would say, is the vertical line test, which may or may not be something you need to do depending on the equation. But it is always good to, do a little reality check. All right. Well, since we learned how to do that, that's, I believe, the last piece of material for, uh, you know, the conceptual part of this worksheet. We're going to do a couple examples here in our last few minutes, but we're pretty close to the end. So, there's no questions. Let's take a look at FNGR 2.2. So the parent function of a quadratic y equals x squared can be transformed across the coordinate plane, as can, all parent functions. Which of the following graphs would represent the parabola shifted 3 units right and 5 units down? So take a second, um, drop your answers in the chat. Seems like we've got pretty good consensus for answer C, which is correct. So if you're going to move right 5, that means you're going to do a little bit of subtraction from subtract from x, which is why we have this subtraction of -5. And then down or move down 3, or sorry, I flipped that around. Move right. It says move right 3. Right. Move right 3. Um, subtract from x, right? My apologies. Move down. It says move down 5, which means we would subtract from y, which is why we're subtracting outside of this little x thing, or sorry, it's the wrong one. We're outside of this little x parentheses thing we've got going on. We're subtracting 5 from y, which is f of x. So yeah, good job, everyone. Seems like we got the right answer. Um, oh, can you guys? Okay, there we go. I just zoomed in. Cool. Light work, light work. Let's take a look at 2.3. So if a of x equals x minus 2, b of x equals 5x plus 4, and c of x equals x squared plus 6x plus 9, find each of these three. So this is kind of like a step one for a lot of problems. Usually you go a little bit deeper and maybe you'd have to graph this, or maybe you'd have to find some information about it, but it is good practice, right? You know, it's a little bit simpler of a problem, but the quicker you get at these kinds of um, like little algebraic things, the easier calculus is going to be for you. So ax times bx is going to be x minus 2 times 5x plus 4, which is equal to, if we do a little bit of FOIL, first, outside, inside, last. Right, so we multiply each of those together, we'll get 5x squared minus 10x plus 4x minus 8, which simplifies down to 5x squared minus 6x minus 8. Moving on, you guys don't have to write out all of these. I know, um, maybe they're super easy for some of you, but just for sake of completion, ax plus bx is going to be x minus 2 plus 5x plus 4, which is going to be equal to 6x plus 2. And finally, number 3, ax plus cx is going to be equal to x minus 2 plus x squared plus 6x plus 9, which is going to be equal to x squared plus 7x plus 7. Any questions with either of those two problems, 2.2 or 2.3? Cool. Cool. Smooth sailing, guys. That's good. Um, we have a few more minutes here. Maybe we might not go all the way to the end, but I do want to just at least glance at these problem sets. This is a typo. This should be, I believe, the FNGR problem set, which is what we're doing right now. But no worries, the problems are still good. Determine if the following functions are either exponential decay or growth. So this is kind of just a memory test, right? How do you tell if it's exponential decay or growth? Well, if I didn't know what the rule was, if I didn't remember what we were talking about earlier, what I would do is just kind of try it out, right? I'd check. So I would be like, okay, if I plug in x equals 0, then f of x, or here we can streamline this, right? So if f of 0 is, let's see, that would be 8 times 1/3 to the x, that would be 8, I believe. I might be wrong, but I believe that's 8. And then we plug in f of 1, we would get 8 over 3. If we plug in f of 2, we would get 8 over 9. Cool. So we do something like that. We do a little bit of plugging and chugging. We'll see that this is decay. However, those of you guys who were paying attention earlier know that any of these multipliers, or sorry, any of these bases that are less than 1 are going to be decay. So anything less than 1 will be decay, and then the rest of them are going to be growth. Because each time you do the next iteration, it'll get either bigger and bigger and bigger, or smaller and smaller and smaller. But remember, you don't need to necessarily remember that rule. You can always just plug in some numbers. And I was able to tell that 8 is bigger than 8 thirds, which is bigger than 8 ninths. And that's how I knew it was decay. Cool. We'll do uh we'll do problem 2 here as well. We got a little bit of time. Given the parent function, f of x equals e to the x. Well, first of all, we'll graph it, just to be clear. Then we're going to shift it left by 3 units, reflect it across the x-axis, then vertically stretch it by a factor of 2. So we're going to do all sorts of things with e to the x. And then we're going to find the equation for it, yeah, ideally. So e to the x looks a little something like this. Well, if x is 1, e should be 2, 2.7, I believe. And then if x is 0, then this would be 1. So we can graph those 2 points. We'll get something like this. Right, so we just so we're clear, f of 0 will be e to the 0. Any number raised to a 0 will be 1. And then f of 1 will be equal to e to the 1, which is equal to 2.7, I believe. Is that true, Nick? Yeah, okay, 2.7. Cool. That's all I got, man. I don't know about all these other numbers of e. That's all you. But it's close enough approximation. A little bit less than 3. So that's e to the x. What about shifting it left by a factor, or shifting it left by 3 units? In order to do that, we're just going to take our same 2 points. So we're going to graph shifting it left. We'll graph a point there, then we'll graph a point there, and then we'll do a similar sort of thing. Then it says reflect across the x-axis. So to do that, we're gonna take that point, which will stay the same. And then we're gonna take this other point. Or sorry, that point won't stay the same. It's not, I was getting confused. It goes over here. Because we're reflecting it across this x-axis. Yeah, so it should stay there. And then the other point will go down to there. We should get a little something that looks like that for this second part. And then last but not least, vertically stretch it by a factor of 2. Wow, Nick, 2.7182. Oh my gosh. I'm assuming that wasn't off the dome, but maybe you just know. Yeah, it wasn't off the dome. Okay, that's okay. How many digits of pi, Nick? I want to see you type out how many digits of pi you can remember.
Give me a sec.
That's give me a sec is crazy. Okay, so he's got a lot. Okay. Nick did say it at the beginning of the last week, guys. He really likes math. And I believe him. Last but not least, we're going to stretch vertically by a factor of 2. So this point over here, which is 1 below the x-axis, is going to go to 2 below the x-axis. And this point is going to go to around there. Should be about 5.4, right? Because that's 2 times, or negative 5.4, because that's 2 times negative e. So with that, we're going to get a little something that looks like that. It's a little bit messy, I know, but that's what they asked us to do. Last but not least, I want to just go ahead and write out what those are. So f of x in the end, so we'll say like f um, sub 3, maybe, just to differentiate it from the original f of x. Um, f sub 3 of x is equal to, the first thing I'm going to do is note which direction is it on? Is it on, or which plane is it on? Is it on the top half or the bottom half? Since we reflected across the x-axis, there's going to be a negative multiplier out in front of whatever we get. Um, and then since we multiplied it by 2, we stretched it. If we stretch it, it's going to be a positive 2 there, as opposed to like a 1/2. That would be like a shrinkage factor. But since we're multiplying it, it'll be 2. And then we, of course, have our e to the x. And since we shifted left by 3, then we are going to add 3. So it's a little bit counterintuitive, but it's going to be like if we shift left, then we're gonna add 3, and if we shift right, we subtract 3. So our final answer should be -2 e to the x plus 3. 3.14159265. Yeah, that's all I got. That's about I can do maybe 3.14159265 3, and then about you got about 20 digits after that, Nick. Very impressive. Very impressive. Math minor by night, math major, minor by day, math major by night. Okay, okay. Good for you, man. Good for you. Cool. Well, the remaining couple problems, there's a whole page of problems left. We've got a similar problem to what we just did. We have a problem, a whole original problem similar to the one that I was kind of looking at earlier, finding the inverse of a problem of an equation, and then another kind of inverse problem, which I do recommend you take a look at. So we're going to end off here in the hopes that you guys do take a look at our solutions, take a look and practice your problems on your own, check back. And if you have any questions, stop by my office hours. Nick, do you have anything else?
Nothing related to this, but I want to say if you guys are interested in math, um, you're all everyone's doing engineering here. If you're one of the engineerings that has to take through Math 20E and Math 18 as part of your major, you can add on a math minor to your whatever you graduate with um, for only 4 additional math classes, upper math classes, 2 of which can overlap with your major classes, and they can all be taken pass, no pass instead of for a letter. So they can't hurt your GPA. So I highly recommend a math minor if you're interested in taking a couple extra math classes. There are some that are definitely easier than others too. But it's just a 4 extra, it's like the easiest minor to get at UCSD. So I recommend. That's it though. Nothing more about this. Exponents and logarithms tomorrow. That's the last of the modules. Probably final review section. Friday. We're almost done. So good job everyone for getting this far, and we'll see you all tomorrow. Peace out.